Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also thought, I didn't have the Nobel Prize for relativity. I ran it for explaining the photoelectric effect. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is the photoelectric effect? The photoelectric effect is the emission of electrons when electromagnetic radiation hits a material. Under the irradiation of electromagnetic waves higher than a certain frequency, the electrons inside certain substance absorb energy and escape to form electric current. That is, light-generated electricity. In classical electromagnetic theory, the photoelectric effect would be attributed to the transfer of energy from the continuous light waves to an electron. The photoelectric effect is divided into photoelectron emission, photoconductive effect, and barrier layer photoelectric effect, also known as photovoltaic effect. The former phenomenon occurs on the surface of the object and is also called the external photoelectric effect or photoemission. The later phenomenon occurs inside the object and is called the internal photoelectric effect. According to particles, light is composed of discrete photons. When a photon irradiates a light-sensitive material, such as selenium, its energy can be absorbed by an electron in the material. After the electron absorbs energy of the photon, the kinetic energy immediately increases. If the kinetic energy is increased enough to overcome the gravitational force of the nucleus on it, it can fly out of the metal surface within 1/billionth of a second and become a photoelectron, forming a photocurrent. In unit time, the greater the number of incident photons, the more photoelectrons will escape, and the stronger the photocurrent. This phenomenon is automatic discharge from light energy to electric energy is called the photoelectric effect. Electrons can only be emitted when the light frequency is greater than a certain critical value, that is, the cutoff frequency, and the corresponding light frequency is called the limit frequency. The critical value depends on the metal material, and the energy of the emitted electrons depends on the wavelength of the light and has nothing to do with the intensity of the light. This cannot be explained by the volatility of light. There is another point that contradicts the volatility of light. That is the instantaneity of the photoelectric effect. According to the volatility theory, if the incident light is weak, the irradiation time will be longer, and the electrons in the metal can accumulate enough energy to fly out of the metal surface. But the fact is that as long as the frequency of light is higher than the limit frequency of metal, no matter how strong or weak the light is, the generation of electrons is almost instantaneous, not exceeding 10 seconds to the -9th power. The correct explanation is that light must be composed of strictly prescribed energy units, like photons or light quanta, related to wavelengths. In 1839, Alexander Becquerel discovered the photovoltaic effect when assisting his father to study the effect of irradiating light waves on the electrolytic cell. In 1873, Willoughby Smith conducted a task related to underwater cables. when testing the high resistance properties of the thelonium cylinder. He found that it has photoconductivity. That is, irradiating the thelonium cylinder with a light beam will increase its conductance. In 1887, German physicist Heinrich Hertz made experiments to observe the photoelectric effect and the emission and reception of electromagnetic waves. From 1888 to 1891, Alexander Stolotov completed many experiments and analysis on the photoelectric effect. He designed a set of experimental equipment, especially suitable for quantitative analysis of photoelectric effect. With this experimental device, he discovered the direct ratio of irradiance to induced photocurrent. In addition, Stolotov and Ricci also joined to study the relationship between photocurrent and air pressure. They found that the lower the air pressure, the greater the photocurrent becomes until the optimal air pressure. Below this optimal air pressure, the greater the air pressure, the lower the photocurrent becomes. Joseph Thomson stated in a speech at the Royal Institution of Great Britain on April 30, 1897, that it was found that the ability of cathode rays to transmit in the air far exceeds that of ordinary automatic-sized particles. In 1899, he irradiated zinc metal with ultraviolet rays and measured the charge-to-mass ratio of the emitted particle to be 7.3 times 10 EMU per Gauss, which roughly coincides with the value of 7.8 times 10 EMU per Gauss for cathode ray particles measured in previous experiments. He therefore correctly concluded that these two particles are the same kind of particles, namely electrons. He also measured the negative charge contained in the particle. From these two data, he successfully calculated the mass of the electron. The Hungarian physicist Philip Leonard discovered in 1900 that ultraviolet light can induce gas ionization. Since this effect occurs widely in the air several centimeters wide, and produces many large positive ions and small negative ions, this phenomenon is naturally interpreted as the photoelectric effect, occurring in solid particles or liquid particles in the gas. In 1902, Leonard published several important experimental results on the photoelectric effect. First, by changing the distance between the ultraviolet light source and the cathode, he found that the number of photoelectrons emitted from the cathode per unit time is proportional to the incident irradiance. Second, using different substances as cathode materials can show that the photoelectrons emitted by each substance have their specific maximum kinetic energy. In other words, the maximum kinetic energy of photoelectrons is related to the spectral composition of light waves. Third, by adjusting the voltage difference between the cathode and anode, he observed that the maximum kinetic energy of photoelectrons is proportional to the cutoff voltage and has nothing to do with irradiance. Since the maximum speed of photoelectron has nothing to do with irradiance, Leonard believes that light waves do not give these electrons any energy. These electrons already have this energy. Light wave plays a role like a trigger. This is Leonard's famous triggering hypothesis. In 1905, Einstein published a paper, a tentative view on the generation and transformation of light, giving another explanation for the photoelectric effect. He described the light beam as a group of discrete quanta, now called photons, rather than continuous waves. Einstein gave another interpretation of the Planck relationship discovered by Max Planck in the study of blackbody radiation. The energy of a photon with frequency f is E equals to hf, where h is the factor of the general Planck's constant. If the frequency of a photon is greater than a certain limit frequency, the photon has enough energy to make an electron escape, causing the photoelectric effect. Einstein's argument explains why the energy of photoelectrons is only related to frequency, not irradiance. Although the irradiance of the beam is very weak, as long as the frequency is high enough, some high-energy photons will be generated to promote the escape of bound electrons. Although the irradiance of the beam is very strong, if the frequency is lower than the limit frequency, it still cannot give out any high-energy photons to promote the escape of bound electrons. Einstein's discourse is very imaginative and convincing, but it has encountered strong resistance from the academic community. This is because it contradicts the wave theory of light expressed by James Maxwell. It cannot explain the refraction and the coherence of light waves. More generally speaking, it contradicts the infinite separability hypothesis of physical systems. Einstein's paper quickly attracted the attention of American physicist Robert Millikan, but he did not agree with Einstein's theory. For the next 10 years, he spent a lot of time doing experiments on the photoelectric effect. He found that increasing the temperature of the cathode would not increase the maximum energy of photoelectrons. He also confirmed that the phenomenon of photoelectric fatigue is caused by impurities generated by oxidation. If the clean cathode can be stored in a high vacuum, this phenomenon will not occur. In 1916, he confirmed that Einstein's theory was correct and directly calculated Planck's constant using the photoelectric effect. According to the wave-particle duality, the photoelectric effect can also be analyzed with the concept of wave without the concept of photon at all. William Lamb and Marlon Scully proved this theory in 1969.